Good evening, everyone. So today we will be continuing our class on design of built-up compression members, and in the previous class we have decided that two ISMC 350 channel sections will be considered for the built-up compression member. So these are the two ISMC channel sections, ISMC 350, and they are separated by a distance of S. Okay, so I have already discussed with you in the previous class that whenever we design a section, we have to make I y dash y dash and I x dash equal to equal. Okay, so that ultimately the compression member becomes stronger in both the directions, because moment of inertia is what is proportional to the strength, and if the moment of inertia is same in both directions, then that means the column is also equally stronger in both directions. So for that we will calculate the value of I x dash at first, and then we will calculate I y dash, and then we will equate it. Okay, so I x dash we can see here. How will we find it? You see, this section is having its own x-axis and this section is having its own x-axis. Okay, and for the built-up compression member, this axis gets merged, so ultimately I for the built-up column, x dash will be the axis, and it will the moment of inertia about the x dash will be equal to the sum of the moment of inertia of each channel section about its x-axis. So it will be ixx here and ixx here, so twice ixx. So we put it like this, and ultimately we get the value of ix dash x dash. So let us go to the iy dash y dash now. For y dash y dash, we have to uh, know one concept which is called as parallel axis theorem. So I'm just showing you the parallel axis theorem here. If we take an element like this, having its y axis in this manner, and if it has a moment of inertia about this axis as iy, and if we have to find out its moment of inertia about another axis which is parallel to this axis and separated by a distance r. Okay, and let us consider that this element has the area a. So the moment of inertia of this element about this axis will be equal to this one. Okay, Iy plus area into distance between this axis. So we have to use this concept. Now let us concentrate on one channel section. Okay, so when we suppose find out the moment of inertia of this section about y dash, if we multiply it by 2, then we will get the total moment of inertia of both the sections about y dash, because these are symmetric. So we have to just find out y dash for this one, and then we just have to multiply it by 2. Okay, so for this one, what we have to do, this y is this one, this y dash is this one. What is r? R is this one, and we know that this is s, so this will be how much? S by 2. So what will be r? R is equal to cyy plus s by 2. Now let us try to write this equation for this channel section. Okay, how will you write it? What is Iyy? Just write down the value of Iyy. We have got it from the steel table. What is the value of A? The value of A is 5366. What is the value of R? This one. And since this is for one channel section, for this is for this one, so for the whole we just have to multiply it by 2. Okay, and CYY also we will get from the steel table. It is 24.4. So this is the y dash value for the built up column section. Okay, so now what we have to do is y dash we have got, x dash we have got. We just have to equate it, and from the equation, just let us see how it looks like. If we equate y dash and x dash, the equation will look like isn't it? So we have to equate this and this, and every value is there except s. So when we equate this with this one, we finally find the value of s. Okay, so I will not do the calculation. You have to do the calculation by yourself. Okay, so you will see that the value of s comes around 218. When you equate this and this, you should know the purpose of why we are equating, because we want to make y dash equal to x dash such that when the moment of inertia are same, the strength is same. Okay, we are trying to make a built-up column having equal strength in both axes. So when you equate this is simple maths. I will not waste time in solving it. You do it yourself. You will find the value of s equal to 218, around 218. I will not tell you the exact value. So if you are finding something else like 150 or 250, then you have to check it. Okay, now since s equal to 218, will not take directly s equal to 218, will take s equal to 220. 2 mm difference will not make any will not matter. Okay, so this will become 220 and this will become 110. Okay, so this is one important step that we have completed to find out the spacing, for which y dash and x dash are same. It means now we are providing a spacing in such a way that the built-up compression member is equally strong in both the directions. Now one thing we must know is the next step is to find out the slenderness ratio. Okay, slenderness ratio of the built-up column. is generally taken as this is the standard procedure. Okay, this is the standard formula. This is the formula for the slenderness ratio of the built-up column as a whole. Now, in some book you will find RZZ here. It doesn't make any difference. It's the same thing. So let us write it down. L effective will be what? K into L. What is RXX? You'll get it in the steel table. So ultimately, how much is the slenderness ratio? You'll get it around 42.8. So you see, slenderness ratio is 42.8 means it is very small, and if the slenderness ratio is small, that means that, sorry, not 42.8. It will actually come at around 45. 45 you will get. Okay, so let us take it as 45. Okay, almost 45. So the slenderness ratio is equal to is very less. That means what? The column is strong. Slenderness ratio is inversely proportional to the strength. If slenderness ratio is small, the column is stronger. If slenderness ratio is more, the column is weaker. Now what we have to do, we have got the slenderness ratio. Then we know that the buckling class of a built-up compression member is C. Buckling class of a built-up compression member is C. So using the table for C, buckling class C, and slenderness ratio is 45, Fy is 250. We can find out FCD. Isn't it? So for FCD we have to use which table, which page number? Page number 42. So we can see here in page number 42 for Fy equal to 250, we have to find out FCD. So just try to find it out. Page number 42. For slenderness ratio 40, the FCD is 198. For slenderness ratio 50, the FCD is 183. So for slenderness ratio 40, what will be the value? It will come as 190.5. Okay, so this is the FCD. Now FCD we know, so what will be the load carrying capacity of the built-up compression member now? What will be the load carrying capacity? It will be FCD into the area, isn't it? So what is the area? Area of one section is how much? 5366. So two sections is 2 into 5366. And FCD we know. So load carrying capacity we can find it in this manner. So 180.5 into 2 into 5366. So ultimately how much it is? Just calculate. or we can say 2044 kilonewton. So this is what? Greater than the applied load, 1200 kilonewton. So we have provided a section which is sufficiently stronger and which can take a load of 2044 kilonewton, which is higher than the applied load of 1200 kilonewton. Okay, so an important step is done. We have decided the spacing. The spacing we have given 220 in such a way that the column is stronger in both directions. Then we have found out the capacity. The capacity is obviously more than the applied load of 1200. Capacity is 2044 kilonewton. The applied load is 1200 kilonewton. So it's okay. Now let us go to the next step, which is called as the lacing. Okay. Now see, when we build up, when we make this column, this built up column, this section and this section, they are not getting connected anywhere, so they are acting as separate entities. So when we have to make them act together. For that, what we have to do, we have to tie them, and for tying them we will use members which are called as lacings. Okay, so for that we have to use another view. You have to look in from this side. Okay, suppose this is the view along the height of the column. Okay, this is the top view and this is the view along the height. Okay, and it is said to us that the height is how much? 9 meter, isn't it? So when it is 9 meter, now it is not acting together, isn't it? So when we have to make it act together, we have to tie them with some members which are called as lacings. So how will they look like? They look like this, you see. I'm just giving you a rough diagram. Okay, so then it's not like there will be just two lacings here. There will be a number of lacings. It depends on the spacing and all. So if I provide the lacing like this, what will it look in the top view? Just imagine how will it look in the top view. Like this, isn't it? So these lacings in the top view, it will look like this, and in the view along the height, it will look in this manner. Okay, this is just a simple diagram I'm showing you. So what we have to do here, we'll not go into the detailed calculation of the lacing because we'll be doing it in the next class, but I will just tell you the objectives. We have to find out the width of the lacing, we have to find out the length, we have to find out the spacing. Okay, we have to find out the thickness. All right, so the things that are important here are width, length, thickness, spacing of the lacings. Okay, so we'll be calculating the value for this, and then what we will do is, after deciding the width, length, thickness, spacing, we will, spacing means this one. Okay, we'll also be deciding the angle of inclination of the lacings, this theta, how much is the inclination of the lacing. Then after finding out these values, we will be checking it for tension and compression. We'll be checking the lacing for tension and compression, and ultimately in that manner we will be reaching the end of the problem. Okay, so till now what we have done, we have decided the sections, channel sections, and we have seen that they can obviously take the compression, but we cannot let them work independently. We have to tie them together so that they can work as one. So we need lacings. So for lacings we have to decide the width, length, thickness, spacing, and also we have to check the lacing for tension and compression. So after in the next class we will be able to do it completely. Okay, so all right, let us not uh, go into a new step now. Okay, we'll be doing this step with a fresh brain in the next class. So thank you everyone for your time.